right, section 9.3. We're going to focus on one last thing in chapter 9, and that is the molecular orbital theory. And the molecular orbital theory is something that we have never covered before. But what the molecular orbital theory does is it helps us take the orbitals that we're dealing with in section 9.2, those s and p orbitals, and it kind of helps us predict whether or not possible bonds of atoms can occur due to the wave nature of electrons. So what you're going to see here is you're going to see bonds versus antibonds. And antibonds just essentially mean that the bonds can exist. So whenever you hear bonding, that means it favors formation, where antibonding is unfavorable. So this diagram is going to combine bonding versus antibonding and kind of determine what you have. So molecular orbital theory is the tool that we use to do this. So like I mentioned, in molecular orbital theory, we're going to study the wave-like nature of electrons and how waves interact constructively or destructively from a physics standpoint. So orbitals, we're going to have orbitals that we either say are bonding or anti-bonding. Well, what the heck does that mean? Well, anti-bonding can exist. So you have two types of you have two options that could happen when when two atoms get together. You could have bonding, which bonding occurs when the energy is low and it's favorable reaction. Anti-bonding is going to occur when the energy is high. Now, that is not going to be a favorable process. High energy, anti-bonding. Pretty much, anti-bonding means exactly what it says. That bond can't exist. So let's take a look at what's going to happen here. We're going to apply the molecular orbital theory. And what we have is we are going to study the molecule H2 in this example. H2. Now, with H, we're just studying the S's. So with S's, all we can have is single bonds. And with single bonds, all we can have is sigma bonds. So we're going to have two types of sigma bonds. We're going to have down below here, we're going to have sigma bonding. And up top, we're going to have sigma anti-bonding. And it's an orbital, so we're going to complete it just like we did before, where two electrons in an orbital complete that orbital. So we have a hydrogen atom here, which has one electron. We have a hydrogen atom over here, which has one electron, because we are bonding hydrogen with hydrogen. We know that that bond exists already, but let's prove it using the molecular orbital theory. This one electron is going to go down right here. This electron's going to go down right here, and we have completely filled one of the sigma orbitals, and we have filled the sigma orbital, which is fully in the bonding shell, which means this could happen. Now, we're going to see something called bond order, and the bond order is 1/2 the difference between the number of bonding and anti-bonding electrons. So if we were to figure out the bond order of hydrogen here, we're going to take 1/2 minus the total number of electrons in our bonding shell, which is 2, minus the total in our anti-bonding shell, which is 0, and the bond order for hydrogen is 1. So therefore, that bond can exist. And we know it exists because we completely filled the bonding shell. Now let's use another example here to show you how this could work later. Let's use helium. We know helium exists elementally as a monatomic molecule. All right, or monotomically, exists by itself. We know that He2 doesn't exist, but that's prove why it doesn't exist. So we're going to do the same exact thing here. We're going to have our sigma bonding on the bottom and our sigma anti-bonding on the top. We have 2 electrons from helium from one atom. We have 2 electrons from another helium atom on the right. These 2 electrons, 1, 2, go here. These 2 electrons, 1, 2, go here. Now you can see we filled our anti-bonding molecule. If we figure out the bond order of helium, it's going to be 1/2, 2 minus H2 is 0, which tells us that He2 as a molecule doesn't exist. So this is kind of using the molecular orbital theory. Now, that is just using the s orbitals. We can combine the p orbitals. So we can have s and p overlap. Now remember, when we have p orbitals, we're going to have the existence of not only sigma bonds like we did, but pi bonds. And because pi bonds can exist in double or triple bonds, it's possible to have 2 pi orbitals on top of the already 1 sigma orbital that we had. So if we look at an S and P diagram, let's take a peek here. You can see here when we have S and P together, our 2s, well, we're just studying the second energy level here. Our s orbital is the same as it was with hydrogen and helium. We're going to have 1 sigma bonding sigma bond. Then we're going to have 1 anti-bonding sigma bond. That's all that can exist for P. When we get to, that's all that can exist for S on the bottom here. However, when we get to P now, we're going to have 3 different orbitals. We're going to have our sigma, we're going to have our 2 pi's, and both of these right here are in the bonding orbitals. Then you're going to move yourself up, and you're going to get what we call the 3 anti-bonding orbitals, 2 pi and 1 sigma. And you can kind of see how they can work. So this is going to kind of show you whether or not something can combine together to form a bond. So this is proving what you kind of knew already, but it's showing in detail. We're going into chemical detail how a bond can occur using the molecular orbital theory. So P blocks have, we know S and P can have sizable interaction because there is that SP overlap. So if we look at the SP interactions and what each of those is going to look like, you can see the behavior of each of those molecules, B2, C2, N2, O2, F2, and Ne2. You can also see that they have labeled something down below here, which was on a worksheet early in the year, but I said we would cover it later. Now we are going to cover it. You see that there's something called paramagnetic and diamagnetic. What does paramagnetic and what does diamagnetic mean? Well, paramagnetic means that there's a single electron in an orbital. There's a single electron available. And the result of something being paramagnetic is it is attracted to a magnetic field. The molecule is attracted to a magnetic field. Then, diamagnetic means that there is a full orbital. There are no singles floating around. All our orbitals are full. And when we have a full orbital, or what we call paired electrons, there is a weak repulsion from a magnetic field. So you can see here, kind of makes sense. Para meaning 1, di meaning 2. Di is going to tell us if the paired, di, 2 electrons together, they're paired. Para is going to mean that they are single. So using the molecular orbital diagram, we can tell characteristics, bond length, and magnetic behavior of our molecules. So we are going to practice with this a little bit with our practice worksheet for section 9.3, but that does conclude section 9.3, understanding and applying how bonds can form or not form using the molecular orbital theory.